Welcome back again to the new learning video. So have you ever wondered how an app goes from, say, 10 users to 10 million without just completely crashing? Well, the secret is almost always hidden in its database architecture. Today, we're diving deep into the essential strategies for database scaling. All right, let's set the scene. Picture this. You've built something amazing. Your launch was a total smash hit, and users are just flocking to your app. I mean, this is the dream, right? Well, turns out this success creates a fantastic new problem. Your single trusty database server, the one that was perfect at the start, is now just groaning under the weight of all that traffic and data. Queries are slowing down to a crawl, and things are getting a little tense. So what's the game plan here? How do you actually architect a system that can handle a truly global user base? Let's break down the 3 core strategies that every single system architect absolutely needs to have in their toolkit. Okay, our first strategy is called partitioning, and you can think of it as a way to tame these truly gigantic tables, all while staying within a single database server. Here's a good way to think about it. Imagine you have a massive single-sheet Excel file with millions and millions of rows. It's super slow, totally unwieldy. Partitioning is basically like splitting that data into organized separate tabs, maybe one for each year, but it's all still inside the same spreadsheet file. It's the exact same data, just a whole lot better organized. So you're going to want to use this when one specific table starts to become a real bottleneck. Maybe it's a huge transaction log or some kind of event table. The beauty is, by partitioning it, your database can just ignore all the pieces it doesn't need for a query, which dramatically speeds things up. And it makes maintenance, like dropping old data, an absolute breeze. And this is just perfect for time series data. I mean, think about it. A log table partitioned by month. If you need to search for something that happened last week, the database only has to scan this month's little piece, not the entire multi-year history. That is a huge, huge performance win. Okay, so here's the crucial point, the catch, if you will. Partitioning is fantastic for organization and performance on a single machine, but it doesn't solve the fundamental problem of that one server being completely overwhelmed by traffic. You're still stuck with the limits of that one machine's CPU, RAM, and disk I/O. And that brings us perfectly to our next strategy, replication. This technique is all about boosting your availability and handling a flood of read requests. The concept here is actually pretty simple, but it's super powerful. Make copies. You've got one main database, often called the primary or the master, that handles all the write operations, like a new user signing up. Then you create one or more identical copies, we call them replicas, that handle all the read operations, like users just browsing content. This is your go-to strategy when your application is read-heavy. Think of a news website or an e-commerce catalog. Way more people are browsing stuff than are actually writing new articles or buying things. It's also critical for high availability, because if your main database goes down, you can just promote a replica to take its place. And this just brilliantly illustrates its power. For a global app, you can place these read replicas in different regions all over the world. So a user in Europe reads from a European server. A user in Asia reads from an Asian server. This massively cuts down latency and makes the user experience so much better. But there's a key trade-off, replication lag. Because the replicas get updated after the primary, there's always a slight delay. This is what we call eventual consistency. Now, for a social media feed, that's totally fine. But for something like an inventory system, it could mean a user sees an item in stock that was actually sold a second ago. Plus, all your writes still have to go through that one primary server, which can become its own bottleneck. So what do you do when even replication isn't enough? When your write traffic is just as massive as your read traffic. Well, for that ultimate scaling challenge, we've got sharding. Now, this is a total paradigm shift. Unlike replication, which duplicates your entire data set, sharding physically splits your data into smaller chunks, or shards, and puts each chunk on a completely separate database server. So one server might have users A through M, and another one has users N through Z. You really only reach for sharding when you've exhausted all your other options. We're talking about situations where your data is in the terabytes or even petabytes, and your write traffic is so intense that a single primary database, no matter how beefy, simply cannot keep up. This right here is the secret sauce behind the world's biggest applications. A social media platform can shard its users by their user ID. A messaging app can distribute conversations across different shards.
This is what lets them scale writes and reads horizontally, almost infinitely, just by adding more servers.
But all this power comes at a steep price: complexity. Your application now has to be smart enough to know which server holds which piece of data. And trying to get information that lives on two different shards, say joining user data with their post data, becomes incredibly difficult and slow. Sharding is an amazingly powerful tool, but it is not one to be used lightly. So how do all three of these strategies work together? Well, the key thing to realize is that they aren't mutually exclusive choices. In fact, the most robust systems use them in layers to build a complete, truly scalable architecture. This table really puts it all together. Just notice how each strategy serves a totally different primary purpose. As you move from left to right, you can see the complexity just jumps from low to high. But then look at the scale rights row. Only sharding gets that green checkmark. That is the trade-off in a nutshell. To scale everything, you have to embrace complexity. In the real world, you would never jump straight to sharding. You'd apply these strategies step by step. Start simple. When a table gets too big, partition it. When your read traffic starts to spike, add some read replicas. And only when your single primary server cannot handle the write load anymore, do you take the plunge and introduce sharding. All right, to wrap all this up, let's look at some essential design tips. Think of this as your cheat sheet for any system design interview or big architectural discussion. This stuff is absolute gold. Keeping these 5 principles in mind will save you so many headaches. I mean, a bad sharding key can create an unbalanced system where one server does all the work. Ignoring replication lag can lead to really confusing bugs for your users. And honestly, aggressive caching can often delay the need for more complex scaling solutions altogether. You see, understanding these patterns empowers you to solve today's scaling problems. But the mark of a great architect isn't just putting out the current fire. It's about anticipating and planning for the next one. Scaling is a continuous journey, not a destination. Thank you so much for watching and digging into these scaling strategies with me. Every system has its own unique bottlenecks, so I would love to hear about the challenges you faced. Let us know down in the comments. And of course, if you enjoyed this breakdown, don't forget to subscribe for more explainers just like this one.